Okay, so we're talking about general equilibrium in an exchange economy. An exchange economy is where each consumer is endowed with a bundle of goods, and the equilibrium is a price point, a price vector, such that when everybody sells all their goods to the market and then makes resulting Walrasian demands, the Walrasian demands are feasible in the sense that they are able to be, there's enough supply to meet everyone's demand. The demand does not exceed the supply. And we're going to ask the three questions about such a thing. Does this equilibrium exist? Are the equilibrium points desirable or efficient? And how do the initial allocations change the resulting equilibrium? So what we're going to do first is just make a mathematical model using the tools we've already developed in this course to analyze this in a slightly more precise fashion. So we're going to say there's K goods and N consumers. So there's always been multiple goods, right? Goods one through N, 1 through K or whatever, the different dimensions of our vector space. That's fine. And now we're just adding in that there's multiple consumers. And each consumer is endowed with some initial stock of each good, right? So that was just this is what I was saying before, that you're given a bundle, right? Now, it could be that each person just produces a different good. We have our banana farmer, and we have our bell pepper farmer, we have our artichoke farmer. It could be that each one has a plot of land devoted to all the things. So the endowments of the consumers are actually vectors, right? It's how much of good one do I have, how much of good two do I have, up to how much of good K do I have. And each consumer has a vector. That vector will be given by the bold-faced omega. So omega is an initial point, which is confusing because omega is the last letter in the Greek alphabet. But omega, the thing that looks like a W, is a bold-faced omega I. Omega subscript I is the endowment of consumer I. The endowment of consumer I is itself a vector, and it determines omega 1i, omega 2i, omega ki, and where each omega ki is the amount of the kth good that consumer I has. There will be n omega bold-faced omega i's, right? One for each consumer. So there'll be omega 1, omega 2, up to omega n. And we can think of that as itself a vector, and that's the endowment of the entire economy. So bold-faced omega with no subscript is a vector of endowments. Each vector of endowments is itself a vector of endowments by each good, right? So horizontally in that, omega with no super subscripts is a matrix. It's a vector of vectors, right? And we can think of that as each column is given by a particular guy, a particular consumer. And then each column corresponds to a row, which tells you how much does that consumer have of that particular good. So each row is good 1, good 2, good 3, good 4, and the columns are consumer I, consumer J, consumer blah, 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 blah. So it's a matrix of size n times k, of rank n times k. Not rank. I don't know what rank means. I don't mean I just mean the size, the number of. We're not doing linear algebra. An allocation is a final consumption. So an allocation is what they end up with, right? So the endowment is your initial allocation. It's what the farmers are born with. The farmers are born with a plot of land that produces artichokes and bell peppers and cherry tomatoes. And the allocation is going to be what they end up with after the equilibrium or whatever, in the end, after some exchange has been made. So it could be that I start out and I just have artichokes, but I really like bell peppers and cherry tomatoes. So I sell some of my artichokes and I buy some of the bell peppers and the cherry tomatoes at the market prices. And so in my final allocation doesn't, in theory, have to have anything to do with my initial endowment. So allocation means after, endowment means before. That's just names. That's not what those things actually mean. In the model, that's what that means. So just as before, each allocation for consumer I is a vector, and it's a vector that says, this is how much of good 1 the guy actually consumes in the end. This is how much of good 2, this is how much of good k. And then we have a vector of allocations for each consumer, and so the allocation for the economy is itself a matrix, right? It's this vector of vectors where each component of the allocation for the economy, x1, x2, xn, is the allocation vector for consumer I, consumer 2, consumer n, and that is what's written here on this slide. So what we're going to say is that an allocation is feasible if this total amount consumed is less than the total amount supplied, right? The total amount that we were endowed with in the beginning. This is just a feasibility constraint. This is just a physical constraint that says, no production happens. So however many bell peppers we're endowed with is how many bell peppers we can eat as an economy. There's no imports, no exports, no anything, right? We're assuming it can be less. We're assuming we can let the bell peppers rot in the field. We don't have to eat them if we don't want them. Of course, we know that we're going to consume all of them because of something that looks a lot like Walras law, looking forward, foreshadowing where we're going. But of course, what we care about here is just we don't have more bell peppers than what we were endowed with. So however many we eat is less than however many we start with. And what is however many we eat means, well, how many does consumer 1 eat? How many does consumer 2 eat? How many does consumer blah, blah, blah? That's x1 plus x2 plus dot, 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 xi plus dot, 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 xn. That's the left-hand side of this equation, the sum over the consumers of their final allocations, how much they consume. That has to be less than the sum over the initial endowments of that same good, right? Which is just summing over the vectors of consumption of each consumer. That's just the allocation of consumer I plus the of consumer 1 plus the allocation of consumer 2 plus the blah 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 allocation of consumer n. That's the right hand side of the equation. Notice that these are vectors. So we're actually adding up column vectors, and we're saying that in each market this has to hold, right? So those are bold-faced x's and bold-faced omegas, which means that the vector of allocations must be less than the vector of endowments, which means that line by line, looking at each market, it must be that we consume less artichokes than we are endowed with. It must be that we consume less bananas than we are endowed with. It must be that we consume less cherry tomatoes than we're endowed with. And these are obviously less than or equal. It's okay for us to consume exactly our endowment. And in the equilibrium that we're going to consider in this class, that will almost always be the case. You will consume the entire endowment because we have strict monothenicity. We like consumption, and just as we didn't want to leave money on the table when we were thinking about this as a consumer's problem, we're not going to want to leave artichokes on the table when artichokes contribute to consumption, when we have strictly monotone preferences. But for now, the physical constraint is just that what we consume, and when I say we, I mean across the end consumers, the total consumption in the economy summed across all of the consumers must be less than the total endowment summed across the consumers. Each consumer is going to be defined as a pair. And the pair is their endowment, which we've already talked about, and a utility function, which we've already talked about a long time ago. The utility function assigns a value to each bundle of consumption, right? It's exactly what we had before. It just takes each bundle of consumption, each vector in RK, which is really RK plus, positive values of consumption, and it returns a utility level, a value for that. And the consumer, as always, likes higher utility bundles rather than lower utility bundles. So the higher U assigns to a particular bundle, the more desirable that bundle is. And we're going to assume that the utilities are very well behaved, and that is that they're continuous, not only quasi-concave, but concave, and strictly monotone. So remember that concavity implies strict concavity. Concavity implies quasi-concavity. So U is a quasi-concave function, which means that it has diminishing marginal rates of substitution and convex upper contour sets, convex indifference curves. And it's strictly monotone. So we're set up to use all of the nice properties that we've already investigated about utility functions, like things like Walras law, things like the uniqueness of the demand, all of that, or convexity of the demand, I guess, come from these assumptions. So we have very nice properties of our utility functions. They're as well behaved as we can possibly want. So as discussed in the previous video, at a given market price, so a market price is a vector in RK, which determines the price in market one and market two up to market K. So that's a price for bell peppers, a price for artichokes, a price for bananas, and the consumer can then convert an endowment into a budget. So how do you convert an endowment into a budget? Well, you sell everything you have. You're given some artichokes, you sell them at the price artichokes. You're given some bananas, you sell them at the price of bananas. You're given some cherry tomatoes, um, you sell them at the price of cherry tomatoes, and that just gives you a budget, and the budget is your wealth, right? It's how much is the value of your inheritance of your endowment, and that's just the price vector times your endowment, right? P dot omega. That's just price of good one times good one, price of good two times good two, the magnitude of the amount of good two, price of good three times blah, 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 blah. So that's just a real number, right? That's a scalar, it's a value, it's a real number. We're assuming that the prices are positive, so this is a positive number. Prices and endowments are both positive. Positive includes zero, but it doesn't include negative numbers. And so the resulting wealth is some positive value. And it's just how much money can you get by converting everything into money, by selling all your goods. And everybody has potentially different endowments. So omega I could look drastically different than omega J, but everyone's price vector is the same. They face the same prices. That's the notion of an equilibrium price. We're in the same economy. If I go to the market and I try to sell my artichokes, I get the same value as if you went to the market and tried to sell your artichokes. Or in other words, if you sold me artichokes, we both sort of agree at the market price that it's whatever I'm paying you per artichoke. And now we can formally define what a Walrasian equilibrium is. So a Walrasian, or general equilibrium in an exchange economy, is exactly an allocation and a price vector. So the allocation is an allocation in each market for each consumer. That says how much of each good does each consumer consume. And the price vector, which is a vector in RK, which is what is the price of each good in each market. So what is the price of artichokes, and then how much artichokes does each consumer get? What is the price of bananas, and then how much bananas does each consumer get? How much blah, blah, blah. We need two things, two constraints. One, that X star is feasible. That means that the amount consumed in this economy is no more than what we started with, right? This is a technical, physical limitation that cannot be overcome because there's no production in this economy. Whatever we start with is what we can consume. So however many bananas get eaten must be less than or equal to the amount of bananas we started with. The interesting constraint is number two, and it says that X star I, the allocation of consumer I in this economy, given the price vector P, must be equal to the Walrasian demand of consumer I. Walrasian demand as the thing we've studied for the first weeks of this class. The Walrasian demand of of consumer I, given the price vector P star, and the wealth that's now endogenized and is the price vector P star times consumer I's initial allocation, endowment. So this is very succinct, right? In the sense that we've now endogenized income. Income is not something that God hands down from the sky. God hands down endowments, and that's turned into income according to the equilibrium prices. So if artichokes go up in price, and I'm the artichoke farmer, I become wealthier. If artichokes go down in price, I become poorer. So my relative income is determined by this price vector, by the equilibrium price vector. Then once I get my income, I make my demands optimally. I decide to choose how many artichokes, how many bananas, how many blah, blah, blah to consume in the optimal fashion. And I'm going to do that by making Walrasian demands. Walrasian demands is a correspondence which said, given my utility function, the price of goods, and my income, this is how much of each good I want. And it was that the price was, it had to be within your budget set, right? Well, here we have all those ingredients. The price is coming from the definition of equilibrium, P star. The income is coming from the price times the endowment, so it's endogenized, but it's still part of the equilibrium. And the utility function we assumed is part of the setup, right? We defined it as part of the economy. So the idea is that we can break this down, and we can think about this in a couple different ways. We can think of the price P as determining how much I can exchange one good for another. I have artichokes and you have bananas. I can trade artichokes for bananas at the relative price of P artichoke divided by P banana. P artichoke by P banana determines the slope of this exchange, the rate of exchange. But equally or equivalently, I could sell my bananas. I could sell my artichokes to the market. I would get money. I would get P artichoke times the amount of artichokes they sell. And then I could buy bananas from the market at P banana times the amount of money I just had. And it would turn out to be the same thing, right? I would be exchanging artichokes for bananas at a ratio of the slope that's determined by P artichoke divided by P banana. So it's a perfectly valid way to think about this, either as individual exchange amongst people at given the market rate at which we can trade bananas to artichokes, or you could think of selling all of your stuff to the market. I sell everything I'm endowed with. I get income P dot omega I, and then I make market demands, not to individual consumers. Everybody sold everything. Now everything's in a pile in the middle, right? Everybody sold their artichokes, their bananas to the farmer's market. The farmer's market's this giant pile of produce, and then we go to the farmer's market as consumers. Like first we went as farmers, we dumped everything on the market at price P, price vector P, then we walked back into the market, we took off our farmer hat, we put on our consumer hat, and then we have our wad of cash that we just got from selling everything, and we spend our money optimally. And what does optimally mean? It means we maximize our utility according to our budget set. Our budget set is now very well defined. It has a price vector and an income. The income is just how much money we got by selling all of our goods to this farmer's market. So what we want from an equilibrium is that the demand in the second stage, in the consumption buying stage, is no more than what was sold in the first stage. All the farmers walk into the farmer's market with their farmer hats on and sell their produce. They walk out, they put on their consumer hats, they walk back in, and they demand that produce back given their money. Well, in order for this to make sense, it must be that their demands do not outsize the amount of produce that's sitting in the farmer's market, which is the sum of all the endowments. So that's just the feasibility constraint. So that's all. We'll stop here now, and we'll talk about how we operationalize this and analyze it in the next lecture.